Okay, if you're watching this, you have hopefully watched the powerful learning opportunity that I said should be watched on an activity called the Hog Hilton, which involves being the manager of a very prestigious hotel called the Hog Hilton, in which you had to book your clients, which are indeed hogs. Now, it sounds really bizarre. I asked students to trust me, and this is where that was ultimately going. This is what that activity was preparing you for, and it's called Electron Configurations. In the past, you understood electron configurations to be, you've done these before, in which you would draw a nucleus with protons and neutrons, and then you would, oh, this is horribly sloppy, but you would draw 2 electrons in the first energy level, and you would draw energy levels, and you would put electrons in. And so I could say that this specific electron is in the second energy level. This specific electron is the first energy level. So we've had a sense of something called electron configurations, which is talking about where electrons are. Now, this is going to take kind of a new look, and it's kind of weird, so just kind of bear with me. There are rules governing the electron configurations, and the good news is that the rules are the same as the piggies in the Hog Hilton. The first one is called the Aufbau Principle, which is essentially pigs are lazy. The second is the Pauli Exclusion Principle, which says that you can have 2 pigs in a room, but they have to be facing in opposite directions. And Hund's rule talks about how if you have more than one room on the same level of a hotel floor, on the same floor, that a little pig will come into a room. Each room will be occupied by 1 pig before it gets paired up. And if this pig is standing on its feet, then this pig, then when it gets doubled up, would have to be lying on its back. So that's Hund's rule. So let's just look at this one more time. This is called an Aufbau diagram. And the Aufbau diagram, I want to make sure that I'm drawing in black. By default, for some reason, it's going to red. The Aufbau diagram really is like the Hog Hilton. So this is the blueprint. This is the blueprint for the Hog Hilton, and that is incredibly sloppy. In this case, now the floors have names. So the first floor would be the 1S floor, and that floor has 1 room. The second floor is called the 2S floor, and that 2S floor has 1 room. The third floor is called the 2P floor, and that floor has 3 rooms. Now, these names do correspond to orbitals. So, and this number right here corresponds to the main energy level. So this is saying at the first energy level, we have an s orbital or a spherical orbital, and that spherical orbital contains 2 electrons. And at the second energy level, we have a spherical orbital, and just a little bit higher in energy, we have 3 p orbitals, and we're going to have the p orbital that is oriented along the vertical axis, the one that is oriented along an x, and then the one that is oriented along a y. So again, those 3 axes represent those p orbitals. And then as you go up the hotel floors, eventually we get into floors that have more than 1 room or more than 3 rooms, and those are your D floors. So this 3D floor is representing electrons that can be found in the 3rd energy level. And so in this case, the analogy is that the pigs represent electrons. So electrons can be found in the 3rd energy level, and at this level, at the 3D energy level, there are 5 rooms. So I am just going to clear the screen and come back to this. So the first rule that we're going to look at is called the Aufbau diagram. And the Aufbau principle says that an electron occupies the lowest energy level that can receive it. So we're going to add electrons the same way that we added the pigs. And we know that in an orbital, we can have two electrons with opposite spins. So a couple things to note here, that 1s is the lowest and the 4s orbital is lower in energy than the 3d orbital. So in the past we would think, well, we have the first energy level, the second energy level is a higher energy level, the third energy level is a higher energy level. It gets kind of complicated here. The 4s orbital, indeed, it takes less energy for electrons to enter that orbit than it does for the 3D, and this has been scientifically backed up with evidence. So I'm just going to pick any element, and you can think of electrons as pigs, you can think of electrons as electrons. So I'm going to take the element lithium. Lithium has 3 electrons. So again, I'm going to use arrows to represent electrons, and if I'm adding electrons, we want to add from the bottom up. So, oh, I don't know what happened there. That was weird. So I'm going to say the first electron is added. We have 3 electrons going to be added in this orbital, and I'm just going to use an up spin first. I tend to put up spins in before down spins. So that's our first electron. If I'm going to be adding the second electron, it's not going to jump up to this level yet, because the Aufbau rule says that an electron will add the lowest occupied energy level that will receive it. So that second electron is going to go into that orbital. And then the third electron is going to go into this orbital. So if I could summarize this for lithium, in the 1s orbital, I have 2 electrons with opposite spins. And in the 2s orbital, I have 1 electron. And I tend to put up spins in first. So this right here is called an orbital diagram or orbital notation. And electron configuration looks like this. What we do is here I'll just write it out, 1s2, 2s1. So I'm just writing what's seen here. In the first energy level, we have an s orbital and it has 2 electrons. Second energy level, we have an s orbital and it has 1 electron. So electron configuration takes on that appearance, and orbital notation looks like this. Sometimes you do see orbital notation written with boxes around it rather than lines, so both ways are examples. All right, so the Pauli exclusion principle says that no 2 electrons in the same atom can have the same set of 4 quantum numbers. Specifically, an orbital can hold 2 electrons of opposite spin. So if we've already really kind of covered this, but let's just go through another example with another element, and let's pick one that's a little bit bigger right now. So let's take 2, 4, 6, 7. Let's do 4. 1, 2, 3, 4, 5. Beryllium, boron. So boron has an atomic number of 5. So there are 5 electrons. So Aufbau principle, if I were to break the Aufbau principle, which is pigs are lazy, I would put my electron here, but I'm not going to do that. So my second electron is going to come here. And now we're talking about that Pauli exclusion principle again. 2 electrons with opposite spin. If I drew my orbitals in like this, this would be breaking the Pauli exclusion principle. We wouldn't see this. Or if I tried to cram 3 electrons in there. So the Pauli exclusion principle says 2 electrons can occupy an orbital, but they must have opposite spin. So let me just finish putting these electrons on. So 3, 4, 5. So my orbital diagram would look like this. I have the 1s and then the 2s, and then I usually draw the p's like this, all three together. The way you can get past that is to actually draw boxes like this. So we have an electron, 2 electrons in this orbital with opposite spins, 2 electrons in this orbital with opposite spins, and then we have 1 electron in the first orbital of the p sublevel. So this is orbital notation, and then the electron configuration would look like this: 1s2, 2s2, 2p1. Now if we were to take boron and draw an electron configuration the way you learned in the past, you would have our nucleus here. In the first energy level, we would have 2 electrons. In the second energy level, we would have a total of 3 electrons. So 1, 2, 3, 4, 5. So if I asked you how many valence electrons there are, you could look at this very easily and say 3. And the same holds true here. At the second energy level, which is our highest energy level, there are 3 valence electrons. 1, 2, 3. So when you look at an electron configuration, you can just count the numbers up on top to indicate which element it is, if that's a question that's ever asked of you. All right, looking at Hund's rule, orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second. All electrons in singly occupied orbitals must have the same spin. So let's just, I'll draw, so let's say that we have the 1s sublevel. I've never drawn boxes before, and I realize that I am kind of enjoying it, actually. I might just continue doing that. In the 2p sublevel, after that there is a 3s sublevel. After that, there is a 3p sublevel, which has 3 orbitals. So let's take an element that is bigger. So we'll look at, let's say, the element aluminum. Aluminum has a total of 13 electrons. So if we put our electrons in 1, 2, 3, 4. Now, orbitals of equal energy are each occupied by 1 electron. So as I'm adding these electrons, I'm going to add them according to the rules. 5, 6, 7. This would be an orbital notation for nitrogen if we were to stop here with 7 electrons. 8. Now we can double them up. 9, 10. And another thing too, all electrons in singly occupied orbitals must have the same spin. So when we were doing the High-Galton, we put the pigs in the room on their feet first. So one pig in each room on its feet. I forgot what element we were doing. Oh, aluminum. So we have 2, 4, 6, 8, 10, 11, 12, 13. Now we could go right up to nitrogen, and nitrogen, phosphorus, I think has 15 electrons. Let's just do one with 15 electrons. I'm going to add the next 2. They would each be added, and every single one of these would have the same spin. So a way that this rule could be broken is one of 2 ways. I could draw an electron in each orbital, but not having the same spin. Or if I have 3 orbitals on a sublevel, I could pair them up before, even though there's a room available, I paired it up. So this would be breaking the Hund's rule. So let's just use the Aufbau diagram one more time to go through an example with an element that's a little bit bigger. And this time we will look at oh, I'll just stop when I'm ready to. So I'm just going to start adding electrons. I'm just having a hard time thinking things off the top of my head. So up spin, down spin. Again, this is the blueprint of the hotel. So the next energy level is the 2s energy level. So 3, 4. The next one is 2p, 5, 6, 7, 8, 9, 10, 3s, 11, 12, going into the 3p, 13, 14, 15. Again, I'm putting one electron in each orbital on the same sublevel, all having the same spin before I start to pair them up. 16, 17, 18. If we were to stop now, we would be at the element argon. Now, one of the biggest mistakes students make here is just to keep following this line, and this is not the blueprint of our energy levels. From the 3p, we go into the 4s. So 18, 19, 20. From the 4s, we go into the 3d. 21, 22, 23, 24, 25. So this would be an element with 25 electrons. And notice that I put all of the electrons, one electron in each orbital before I start to pair them up, and they all have the same spin. Hund's rule. 26, 27, 28, 29, 30. The next is the 4p sublevel. 31, 32, 33. And I'm going to stop there at element 33, which is arsenic. It has 33 electrons. Now, if I'm going to do an orbital diagram, I can draw the 1s, and then the 2s, 2p, 3s, 3p, 4s, 3d, and this is getting really crowded, and then 4p. And the 4p part would end up looking like this with one electron in each orbital, all with upspins. And I'm not going to draw them all in. What I am going to do is I am going to write the electron configuration for arsenic, which is, now if I'm assuming that these would all be filled. I'm not just going to, I don't have time to do that right now. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p3. So arsenic, again, this is the electron configuration. For arsenic, element number 33. And this is the only element that has this configuration. So this is telling us that, okay, in the first energy level, there are 2 electrons. They're in an s orbital. In the second energy level, there are a total of 8 electrons. There are 2 of those electrons in a spherical s orbital. 6 of those electrons are in each of 3p orbitals. At the third energy level, we actually have a total of, we've got 8 electrons here, plus another 10 here, so we have a total of 18 electrons at the third energy level. At the fourth energy level, we have a total of 5. So if I were to ask how many valence electrons are in arsenic, you could look at these two highest occupied energy levels. Those are your valence electrons, and there are a total of 5 valence electrons. So that is going to conclude this tutorial. We will practice a lot in class. And if you have any questions, I would be happy to help you.